Hello again. Welcome to video number 4 about metaprogramming in Lean. In some ways, this is the hardest video to do. We're about to hit a new level of abstraction, the tactic monad. So I'm emphatically not going to try to teach you what a monad is. I'm not going to give you too many details about the notation we're going to use. If you've done any monadic programming in Haskell, it's just like that. Really, a lot of the syntax is stolen from Haskell. There are more than enough monad tutorials online. There's even a Lean-specific description of the tactic monad that's linked in the description below in this video. I want to give you the bare minimum that you need to understand what's going on here and to do a little bit with it. In our previous video, we saw how to manipulate Lean expressions, but our manipulations weren't context-aware. For instance, we couldn't tell if an expression was well-formed or not. So we'd like to write functions that can query and manipulate the global context and the local context if we're in the middle of a proof. We want to know what things have been defined before. We want to know what variables have we introduced in this particular proof. But the problem is that Lean is a pure functional language. So we can't directly interact with the global state like this, otherwise we wouldn't be writing pure functions. We could pass around some kind of state object, but that's super inconvenient when we want to compose a whole bunch of functions that are manipulating the state. So the tactic monad is an abstraction for exactly this kind of stateful programming. We're going to write terms whose type is tactic nat, or tactic expr, tactic unit. A term of type tactic nat is a function that takes as input a tactic state, and it returns a natural number paired with a new tactic state. We have notation that will let us hide these tactic state arguments. So when we work within the tactic monad, we basically get to treat the function just as something that returns a nat. We ignore the input tactic state, and we ignore the output tactic state. Let's start by looking at some of the simplest tactics we know. The very simplest tactic, in fact, it exists in all monads, is return, also known as pure. So I'm going to create a function of type tactic nat. Call it make nat. I'm going to define this function as just return some random number. What return does is it lifts a value, in this case a value of type nat, into the tactic monad. So from some value, 14, which is just of type nat, we get something of type tactic nat. In fact, return is more general than this. If we look at its type signature, we see that it applies to any monad. It's a way of introducing ground values into the monad. The second simplest tactic that we can talk about is called trace. I have the tactic namespace open, but there's something else called trace as well. So I'm explicitly writing tactic.trace here. Usually we don't have to write tactic. We see the type of tactic.trace is, well, something to tactic unit if we see the full type. In fact, anything that has an instance of has to tactic format can be traced. In practice, everything we deal with will have this instance. So what trace does is it takes in a value, it prints it to our output window, and tactic unit means that it doesn't really return anything. Unit is just the type that has one element. So we don't care about its output. We care about its side effect, which is printing to our info view. So let's write a second tactic. Trace_nat is going to have type tactic unit. And here I'm going to use something called do notation. Do notation allows me to interact with the tactic monad to get values, as I said before, without passing this state around. So when I'm trying to define something of type tactic unit, I'm able to use this. what I can say is do n gets the left arrow. I can type that using \L. N gets the value from makeAnat, and then we want to trace n. The do notation is allowing me to compose tactics. makeAnat has typed tactic n, so this is assigning the natural number n to whatever makeAnat returns. And after this, in my context here, if I comment this line, I see that I have a natural number n in my context, and Lean is expecting something of type tactic unit. Well, trace has typed tactic unit, or trace n has typed tactic unit. So I'm getting a value from one monadic function and then calling a new monadic function. In the end, this gives me something of type tactic unit. The type of the entire do block, roughly speaking, will be the type of the last line that appears. So this is type tactic unit, just like trace n. How do I evaluate this? I want to see what my tactic does. Well, remember, something of type tactic unit is a function that takes in a tactic state, and it produces a new tactic state, as well as something of type unit, which we don't really care about. So we need to create a tactic state somehow to call this. And there are a few ways. The simplest way we can do this is using the run command. Run command traceAnat creates what's sort of like an empty tactic state, kind of no extra information there. And it traces over here the number 14. So that's good. Another way that we can see this with a little more control over what the tactic state looks like, we can say example, maybe I want some stuff in my context, some integers ABC. My goal doesn't matter so much for now. Maybe I'll try to prove false, which I can't do. And here's a begin end block. And I can call traceAnat here. Again, I see the output 14. There are some complications that we'll address a little bit later with using these begin end blocks. Your tactics might not behave exactly like you've seen other tactics behave. So for the rest of this demo, I'm going to prefer run command when it makes sense. But sometimes we'll need some extra stuff in here. In order to avoid this parsing stuff that I mentioned, one final way to do this, which is the preferred way to do an example for this demo, say by do traceAnat. And again, we see the output 14, and our tactic fails because I haven't closed my goal of proving false, of course. So these are some very basic tactics. What are some other useful tactics? Well, tactics are operating on a proof state, we said, on a tactic state. It'd be nice if we could see that tactic state. So there's a built-in tactic called trace state. The output of trace state we see up here, the text version of what we have down here, and it just kind of prints the context, like in the goal window. It tells us we have 3 integers in our context, and our goal is to prove false. What is the type of trace state? It's tactic unit. For the rest of these first examples, instead of writing them by do blah, blah, blah like this, I'm going to define some extra tactics up here. Metadef inspect. What if I want to look at the goal in particular? I should have a way, if I have access to the entire tactic state, I should have a way to figure out what I'm trying to prove. That tactic is called target. What is the type of target? It's tactic expr. Remember the expr type from the last video. So I can assign the output of this tactic, which basically looks in the tactic state and gets the goal. I can assign it to a variable t. Now I have something of type expr in my context. I want something of type tactic unit. So why don't I trace it? So let's inspect. And OK, that's good. We've printed false. That was our goal. If I change this to a equals b, then the output of inspect becomes a equals b. At this point, t is just some expr. Comment this and show you. T is just an expression. All of the expression manipulation stuff that we talked about in the last video, we can now do to t. If I have a function expr to expr, I could manipulate this thing t, and it would be like I'm manipulating the expression a equals b when I apply my tactic down here. What are some other things that we can do? We can trace the target. What about the variables abc in the local context? Maybe I want to access the variable a. I can do that by using the tactic getLocal. What is the type of getLocal, though? It has type name to tactic expr. So it's going to produce an expression, which it turns out will be a local constant, but I need to give it a name. We might be tempted to say getLocal a, but remember, a is not a name. In fact, a is just a variable that's not in scope at all here. To make it a name, we have to give it a backtick. So this is saying get the thing in the local context that has the name a. And maybe you want to trace a expr. So now it traces a. That's good. But just tracing a is maybe not so interesting. What is a, really? Maybe you want to trace expr.toRaw format of a expr. Remember from the last video that this was the full form of expr, and it gives us some crazy output. It's a local constant. So this is the unique name. Its pretty printing name is a, and then there's some other nonsense. We won't worry about that. OK, cool, cool. What is the type of a? This was something that was kind of hard for us to get. If we were just dealing with expressions, they weren't really type aware necessarily. But there's a tactic called infer type. A expr. The type of infer type, well, it's expr to tactic expr. Remember, types are expressions, just like terms. So let's assign this to a type. And let's trace a type. Good. The type of a is int. Well, that's great. Exactly what we expected. What if I want to get all of the variables in the local context? I can do that too. A tactic called local context. And trace CTX. What is local context going to return? It returns a list of expressions. Well, that's new. CTX is a list of expressions, so when I trace a list, I get the list A, B, and C. OK, well, all good so far. We can get expressions, we can infer their types, but I see something that could go wrong here. I wrote the tactic inspect before I wrote my example where I apply it. Inspect looks for something in the context that's named A. But what if there were nothing in the context named A? I'll change that one to C, and I'll delete this. What happens when I try to run the tactic that gets the thing called A and then prints its type? Well, my output has changed. I now see the target, but I've lost all of those other trace outputs. Instead, I see an error down here. It's different from my error before. It says the get local tactic failed. There's nothing called A in the local context. So tactics are not guaranteed to succeed. This is another aspect of the tactic monad. If a tactic doesn't do what it's supposed to do, it doesn't have to return a default value in order to remain a pure function. It can fail. And if any of these tactics in our sequence here fails, then the rest don't get executed. We stop our execution at the moment of failure and produce some failure message. So we failed at this line here. What if I wanted to be a little clearer about what went wrong? If I wanted to write my own failure message, I could do that like this. This is a tactic combinator. It's an or-else combinator. So it says, try to do this first. If that doesn't work, then do this. So what's the alternative that I gave it here? Well, it's still failure. So this failed. This is going to fail as well, but this time I'll fail with a different message. And we see that here. Oops, no A. Maybe instead of failing with the message, I want to return some default value. I'm going to say, look for A. If it doesn't exist, then give something else. I can give it some random expression, maybe the natural number 0. And what do we see now? Well, everything has succeeded. A_expr is now the constant 0. This is the raw format, and it has type nat. So it failed to find the local A, but instead, we gave it this default value 0. A few more things that I want to point out here about living in the tactic monad. These assignments, they only work for tactic valued things. Local context was tactic list expr. Infer type was expr to tactic expr. What if I just want to assign some value? New nat, and I'm going to give it 40. Well, there's an error here. It's not the easiest error to understand, but we can kind of look at this and see, well, this isn't tactic nat. This is just a nat. If I wanted to do this, I would have to write return 40, and then things work. I see 40 gets traced at the bottom. But another way to do this would be to use a let expression. This works in our do notation as well. I can say let new nat be 40, and then trace it. And we see the output we expect. We only use this left arrow to get the result of some tactic call. We say execute this tactic and assign the result to the name context, for example, ctx. If we're not actually executing a tactic, we're just providing some value like 40, then we don't need to use the left assign or get operator, whatever we want to call it. We can just use our familiar let. A final thing to point out about working in the tactic monad is writing loops. All of these steps have kind of just executed one single tactic. We used infer type here on A, which was one value that we got from our local context, and I'm going to add it back here. We inferred the type of A and found that it was a nat. But what if I wanted to infer the type of everything in my local context? Maybe I'll add some stuff here, some integers. At this line, I have the local context. I've called it ctx. But how do I loop over the context and infer the type of every value? There are a few very useful functions here that are actually functions on lists. that we can use for this. So CTX is type list expr. Even before I write it, I'm going to check list.mmap up here. And it's easier to check it fully elaborated. We take some function m, which is a monad. I'm going to take a list of values of alpha and a function that takes in an alpha and returns something of type m beta. If we're reading m as tactic, this is a function that takes in a value of alpha and produces something of type beta within the tactic monad. And this gives us something of type tactic list beta. A little abstract. Let's do it in context here. Let's say CTX primed gets ctx.mmap. I'm going to use the use projection notation to say list.mmap ctx. What are we expecting here? Well, this should be a function that takes in an expression, an e, and it should produce something of type tactic something else. Let me say infer type e to make this actually elaborate. So I take in an expression, e, infer type is type tactic expr. So what this whole call is doing is looping over the list ctx, which is a list of expressions, and it's applying infer type to every element of that list. In the end, I get ctx as a new list of expressions, and when I see it traced, everything was an int. Maybe just to show some differences here, let's make that nat. And then we see I have 3 integers, 2 natural numbers. So I've applied this monadic value function, infer type, to every element of my list. Maybe I could do this map and trace in one step. I'm going to go back to CTX, and I'm going to use a very slightly different function, list.mmap primed. What does that do? It takes a list of alphas, takes a function that takes in an alpha and returns something of type, let's say, tactic beta. But its output isn't tactic list beta. Its output is tactic unit. This means that we're not actually looking for the result. Instead, we're just looking for the side effects of the result. So what I can write here is ctx dot mmap primed. And again, I'm going to take an expression e. It's not sure what we're expecting, but I can write a new do block here. I want something of type tactic unit to go into this block. So I can write something of type tactic unit using do notation. I can say do type gets infer type e, and then trace the type. So instead of getting a list of types that I got up here, for every element of the list, I've traced its type. I've said map over my list with this monadic function. So every element in our list CTX, we find its type and we trace it. This is a very, very useful paradigm when we're writing tactics. Really, in any kind of programming language, we like to be able to write loops. And this is a way to write a monadic loop. So this video was to get you familiar with the tactic monad. Our next video will implement some more interesting examples than we've done here. And I think we'll have one final video after that, which clarifies some subtle points about tactic.